First, we're going to discuss the equation for this result. And if you can remember, and let's take a parallel, we had this equation for the convection, right? And this was the heat flow. If you wanted to remove this area, you would get heat flow per unit area. If you divide this by area, you get, and that's usually written as smaller q. But anyways, this is convection. So radiation also has a very similar results. But there are some things which are slightly different. We're not going to go into everything, but some things are cool. And the thing about radiation is that it, convection was a linear response. Difference in temperature, difference in the cold temperature is going to affect how fast your temperature leaves. If it's a really cold day, you're going to lose heat faster than if it's 60 degrees outside, you're going to lose heat at a certain rate, which is going to be slower than if it was like 0 degrees or negative 20 degrees Celsius. You're going to be freezing, and you're going to lose a lot of heat. So this is a linear relationship, as you see here, but radiation, one of the big differences is that it's a quadratic relationship between the surrounding temperature, which I'm calling Tc, and the heated object, which is I'm going to call Th. This is not quadratic; it's to the 4th power. So that's one effect here, and the next effect is so with radiation, we have something called the emissivity coefficient, and there's also another coefficient here, which is sort of like a constant, which comes from the science of radiation and heat loss and how heat can be lost through light. A hot object loses heat both through convection, and if it's just sitting out in the open without any fan blowing or water flowing, it's natural convection, and it's also losing heat through radiation. So if the temperature of the room and U has a small difference, the convection coefficient will sort of dominate the result. However, because this is to the 4th power, as you increase, I'll just give you an example. So if we were to say radiation is the blue one, radiation heat loss, and this is a general sort of understanding, and this is the change in temperature between the outside T and Th. So if we see the difference in temperature, how the heat rises, it's going to go like that. It's going to be a quadratic relationship. But for the convection, it'll be a straight line, right? So at some point, the convection will take over, will be more. But usually with piezos, you're working sort of in this range, where convection does add some, but neglecting it, it's not such a big deal, as long as you can sort of make up for it by linearizing it and including it in the convection coefficient. So again, there's two types of heat loss which can occur: convection and radiation. Convection can either be forced, or natural convection, which is just something sitting in the air and it loses heat due to the rising and falling of air, which is hotter and colder. Difference in densities result in some type of spinning air motion. You can find some ideas about online. You sort of see it with your tea or your coffee, how the water vapor swirls around, and that changes actually induces a sort of a flow of air, which makes it called natural convection. There's also conduction through air, but that's not really important. So, and the next way to lose heat is called through radiation. And radiation is basically losing heat through light loss, sort of. So a hot object in a cold room loses heat to its surroundings by emitting light. You can read the details about it later. But it has a relationship related to the hot and cold temperature to the 4th power. Therefore, it sort of picks up speed at a higher temperature. We can expect the heat loss due to radiation to be much more than the heat loss due to convection at a very high temperature. And just like we had the convection coefficient, which told us what's the intensity of the heat loss, a strong fan versus a low fan versus an object sitting on open still air. These all have lower convection coefficients. Or flowing water, he has even more. That's why you probably freeze in, like, if you jump in, like, let's say if you step outside in 0-degree air, it's going to be pretty cold. But if you step out in 0-degree water, you're going to freeze immediately because the heat loss is more, because the convection coefficient is much higher in water than it is in air. So the other term which we would like to discuss with regards to radiation is this term here. It's called the emissivity. And the emissivity, when we spoke about radiation having to do with light. So emissivity has to do with a material's ability to emit and reflect light. See, basically what happens is that all objects are emitting light. So if I have one object at T1 and I have an object at T2, let's say these are the only two objects in the universe. So if T1 is equal to T2, light is coming off of T1, it's hitting T2 and being absorbed. And light is coming off of T2 and it's hitting T1 and being absorbed. Because equal amounts of light are being absorbed and produced, there's no heat transfer. However, if you had two materials, and this is sort of getting confusing maybe now, if you had two materials, and let's say this is a very shiny ball, and it's at and this is at, okay, let's cancel that explanation. Let's say T1 was greater than T2, so we had this again, T1 and T2. Then the light coming off from T1, which is here, is more than light coming off from T2. Therefore, there would be a net heat transfer from T1 to T2 due to this light transfer. Do you heat the fire or the fire heats you? The fire heats you because the fire is hotter than you. You are both emitting light as physical objects, which have some type of temperature. You're both emitting some type of light, but the fire is emitting more light than you are. Therefore, it's winning, sort of. You're not heating the fire is heating you. Another thing to consider here is that coefficient I called emissivity. And let's take the same case where we have T1 is greater than T2. That's not exactly a T, is it now? Let's draw it clearly here. T1 is greater than T2, and we have T1 here and T2 here. And as I said, the heat transfer is going to happen in this direction. Although heat transfer is happening both directions, the net heat transfer is happening in this one because there's more light coming off of T1 than T2. But and I mentioned that when light is emitted, it also has to be absorbed, right? It also has to be absorbed. So let's say T1 was a shiny metal ball, or let's say T2 was a shiny metal ball. Let's make it like this color, right? And T1 is a black ball. You can't see black here, so I'm just going to draw a circle. Okay. So now what's going to happen? I'm going to call this case A, QA, and I'm going to call this QB. In which case would the heat transfer be more? In QA or QB, where this was a shiny metal ball, or they were both sort of the same color? The actual it ends up being that because this is shiny, some of the heat or some of the light which is coming here is directly reflected off. And because it's reflected, not as much heat can be absorbed, therefore not as much heat is transferred. And this is the measure of emissivity. Emissivity, in layman's terms, is the measure of how well a material emits and reflects light at more or less infrared radiation. So if you have a shiny silver, which also reflects, it's going to have a low emissivity, maybe of 0.15. And if you're going to have like a black paint, assuming it's black to, black absorbed light, we're going to have an emissivity around 0.95. So basically, by changing your surface, of your material, assuming this was a metal ball or this was a black ball, you're going to be changing the interaction between the heat transfer. And this is an important concept to know when you are trying to measure temperature using a thermal camera. Let's go through a final example here. Let's say both of them are shiny metal balls. yeah, let's say T1 is equal to greater than T2. And obviously the heat transfer is going this direction. I'm going to call this the case A. This is T1 and this is T2. And let's say this is a piezoelectric element, and I want to reduce its temperature. And let's say this is the way I would be able to increase the amount of heat flow from T1 to T2 is how? Oh, okay, and this is shiny, right? The whole thing should be shiny. The way I can do it is if I cover it with a black paint, then it's actually going to emit more light, because there's also internal reflections happening inside. So I would be able to more light would be able to escape and go into the T2 ball anyway. So more light would be emitted due to the change in color. This has to do with the change in emissivity. And remember, this is not visible light we're talking about. We're talking about infrared light. So if we're talking about shiny, we're talking about shiny toward infrared light. Or if we're talking about black, we're talking about black toward infrared light. Typically, they do coincide, like aluminum foil is shiny to visible light, and it's also shiny to infrared light, also reflects it, has low emissivity. So this concept is very important for that reason. The next concept we're going to talk about is heat generation. And heat generation